Hooray! So we understand something about how gravity affects light, how gravity affects time, because we're dealing in a relativistic theory. It affects distances as well. And Einstein thinks when he figures this out that he's well on his way to resolving the theory. It turns out that the mathematics involved is difficult. Luckily for him, unlike Newton, after a few years of worrying about it, he discovers that mathematicians had already pretty much solved the problem he was trying to solve, albeit in a different context, and making the connection in conversations with Riemann, he very quickly is led to what becomes the theory of general relativity. And he comes up with this understanding that gravity is, in a very technical sense, a description of geometry. And as I said, the mathematics was hairy, and we're not going to do it here, so this is the hard part of the class where I get to do a lot of vigorous hand flapping and tell you the answers, but I'll try to motivate it. So what do we know about gravity? What are the characteristics of a relativistic theory of gravity? Well, in small regions of space-time, if you observe, there are a collection of inertial, freely falling observers, and if they measure, then in their local region they claim that there is no gravity. These are the freely falling observers. Of course, there are many of them. They can have all different velocities, and their different experiences locally, because they have constant relative velocities relative to each other, are related by the Lorentz transformations that we know about. And then the reason that gravity is for real, what's really going on, is the tidal effect, the fact that the acceleration of gravity at different positions in space and at different times is not the same. This means that what is an inertial observer here is not the same as what is an inertial observer there. So if two people are freely falling towards Earth, say, near to each other, they jump off the same spaceship, and they're freely falling towards Earth, they will notice that they are slowly accelerating towards each other, and each will blame the other for being not inertial. I'm in free fall. You can't be because you're accelerating towards me. Of course, what's really going on is they're both accelerating towards the center of the Earth, and it's that tidal effect that is the real gravity. On the other hand, if I give an object a velocity, any initial velocity at any given point, and then just let it go, then gravitation ensures that it knows where it's going to go. At that point, gravity is the only force acting. So given any initial velocity, there is a unique inertial world line that starts with that initial velocity, starts moving at that slope relative to the vertical axis, and then from there on, let gravity do it. Gravity will tell this thing where to go. Why am I telling you all these stories? These are all things we know, because they all have an analogy in these theories of geometry that were being developed in the 19th and early 20th century. And what do we know about, what do these people teach us about geometry? You're talking about the geometry of curved spaces, and we'll give an example and try to make it more clear. But small regions of a curved space always appear like flat space and can be described with the normal x, y, z, whatever number of coordinates your dimension is. We all live on a curved space, for example, the surface of the Earth, but we all use coordinates like street and avenue number in the context of a city, and we can easily describe Manhattan ignoring the curvature of the Earth and navigate around Manhattan to very good precision, because the curvature of the Earth affects us only over large distances. A small chunk of the Earth, of the spherical Earth, is effectively flat, and we can use maps. But we can't use a map, as we all know when you look at trying to draw projections. A map of the entire Earth needs to be either a globe or have large distortions on it. Now again, just as with gravity, when you sit at any point on a curved surface, you can draw these little straight lines, and pretending that things are flat, pick any direction. You can draw the beginnings of a straight line in any direction in the little flat region, and those lines are related by rotations. You rotate a line through one point in one direction, you rotate it, you get a line in a different direction. On the other hand, the lines that are straight in these local patches, in one little piece of the space, are not, and we'll see this, the same as the straight, do not look straight as viewed from different position, and in particular are not related to the straight lines through this point, the first point by rotation. And third, given a point in an initial direction, there is a unique geodesic, the analog in a curved space of a straight line. And we'll see an example of how to do that. But in any curved manifold, at any point, there is sort of this analog of the straightest thing there is, the closest there is to a straight line. It's a well-defined geometric object. It's called the geodesic. And at any point, if you pick a direction, there is a unique geodesic that starts at that point, moving in that direction, just as there was a unique inertial world line starting at any point with any velocity. You're beginning to make the analogy, and the shape of a space is encoded exactly in the fact that what are straight, that if it's curved, that what are straight lines at one point are not straight lines at another, or it's encoded in the distance between points as some, of course, the distances between points depends how you label the points, but there's some coordinate invariant information there, and in geometric terms, this is called curvature. This is a lot of fancy words about geometry, but I haven't really told you anything. Let's do an example that might help us understand what we are talking about. And the example is, let's think about Earth's surface. It's a two-dimensional surface. We live on a surface, and it's a curved space. The surface of a sphere is not flat. Try to wrap a piece of paper around a ball, or make a planar, a map, two-dimensional map of the Earth on a flat piece of paper, and you'll realize that the Earth is curved. To a good approximation, it's spherical. Spherical is special, and it makes some of the observations sort of trivial. On a sphere, every point is the same as every other. And so if we think of the Earth as a sphere, then might as well start at the pole, because we want a point. Every point is like any other. If you start at the pole and you head off in any direction, you're going south. And now we understand on Earth exactly what it means to go in a straight line. Sit at the pole, pick some direction, and keep going straight. What are you going to do? Well, you'll start out heading south along some meridian, and following that meridian would be going in a straight line. Turning east or west of that meridian would not be going in a straight line. We all have this understanding, and eventually, of course, you'll come to cross the other pole, keep going around the Earth, and come back to the place you started. What you will have completed is what is called a great circle. These are those geodesics that I talked about, and you notice that starting at the pole, going off in any direction, there are meridians that are these great circles. Nothing special about the pole. As I said, every point is like every other point. So indeed, on Earth, there are precisely straight lines, great circles, geodesics, unique ones starting at any point, heading off in any direction. Now initially, as you imagine a bunch of penguins walking off from the exact North Pole in all directions, they won't notice they're on a curved planet. They will be walking on a straight sheet of ice, and everything will look completely flat, and in particular, if they measure the distances between them, they will match what you would expect from the small angle approximation if they're moving at small angles to each other, and the distance they've traveled. As they get farther and farther away, they will find that each successive penguin is farther and farther apart. On the other hand, as they get really far, they'll notice that the distances are not increasing sufficiently. This is where the curvature of Earth comes in, and perhaps a demonstration of this would be helpful. So here's our demonstration. It's our old friend, the right ascension declination demonstrator from UNL, but we're going to repurpose it for what our own devious goals here. And so what we're going to do is we're going to imagine this collection of ants or penguins that we talked about. They start at the North Pole, and as they move off in all directions, initially they don't notice the curvature of the Earth. And what that means is that one walks along the green meridian, one walks along the red meridian, and they will notice that the distance between them is given by the distance they have traveled, and then determined by the small angle formula and the angle between them. But as they get farther and farther apart, you notice that these lines, here's the one of the penguins, as they get farther and farther down their lines, they'll notice that their lines are not getting separated by a sufficient distance. They're in fact failing to get to be far enough to satisfy the small angle formula. In fact, as they go farther, the distance stops increasing altogether when they hit the pole, and then it starts the equator, and then it starts decreasing, and eventually these two lines that went off at different angles do something they would never do in a flat planar world. They collide again at the South Pole. So the fact that these two geodesics are not going far away enough from each other, not going as far from each other as they would in the plane, and that eventually they meet, is an indication of what we call the positive curvature of the surface of the Earth. Lest we get too caught up in all curved surfaces are like the surface of the Earth, we have here this nice demonstration of a surface, again, two-dimensional. We can only really imagine curved two-dimensional spaces because we think of them as sitting inside our three-dimensional space, but there are curved 3 and 4 and 6-dimensional spaces, at least mathematically. And so you can, this surface, this so-called one-sheeted hyperboloid, is a surface with a negative curvature, and I'll make it a little more transparent so we can see, and the geodesic that I'm this program very nicely draws geodesics through a chosen point, and I can vary both the location of the point and the angle. What I want you to see is what happens when I make a small change in the initial angle. See, I'm rotating the initial angle at which this geodesic comes out ever so slightly, and what I'm seeing is that geodesics that start very nearby here are, notice that the change far off is much larger than the change I'm making nearby. So geodesics that start very near each other will eventually grow very far. The distance between geodesics grows more than you would expect on the plane. These are getting farther apart more than the small angle formula specifies. A negative curvature leads to diverging geodesics, whereas a positive curvature leads to converging geodesics, as they do on the surface of the Earth. So we have here this analogy between geometry, for which we have some intuition and for which mathematicians had the formalism, and the theory of relativistic gravity. The role of inertial world lines is played by geodesics. Lorentz transformations correspond to rotations. Rotations preserve the distance between 2 points. We know that making a rotation does not change the lengths of things. Lorentz transformations also preserve something. They preserve the value of this invariant interval that we defined. The minus sign here, as opposed to the plus sign here, has an important role. It means that the geometry, technically, we're going to describe as pseudo-Riemannian rather than Riemannian, and it makes many differences. Gravity is not the same as the description of curved Riemannian spaces, but gravitational forces are therefore the changes in the fact that the tidal forces that make what seems to be inertial at one point not look inertial at another point play the role of the curvature. So the idea is the presence of a massive object deforms space-time in its vicinity, and the motion of inertial, freely falling objects is along geodesics, these straightest of lines that you can draw. Remember, inertial world lines were those straight lines in the flat case, absent gravity, and now they're going to be as straight as they can be in this curved space-time. And the picture that is often brought up as a visualization is this rubber sheet image. You put a bowling ball in the middle of a rubber sheet, it bends the rubber sheet down, and then rolling a ping pong ball will cause the ping pong ball to move around it. This is misleading on a whole number of levels, but it gets the general intuition in there. In some sense, the presence of a massive object, in particular the main ingredient here that is completely absent from the real case, is gravitational field of the Earth pulling the bowling ball down. This preferred down direction is completely non-existent in the actual case, but I will give you a better visualization in a minute. A few caveats to taking this picture too seriously. First of all, the shape of that deformed surface, the rubber sheet, is not related to curved spacetime. I'll describe the curved spacetime in a minute. In general relativity, it is not space that deforms, but space-time, this four-dimensional object, or if you want, that in the two-dimensional case that we've been drawing, the whole two-dimensional sheet is curved, not just the x-axis. It's not space that is curving, it is space-time. In some circumstances, particular cases called static spacetimes, where nothing changes, essentially, in a static spacetime, you can define something called space and think of space at any given time as we could think of the entire universe at any given time, those horizontal lines in our space-time diagrams. Those make sense in the sense that all of these horizontal lines are essentially the same in the static space-time case, but not always. Most of the space-times we'll need to consider are going to be static. Inertial orbits are, when you look at this space, the inertial orbits, the ellipses with the sun at one focus, are not geodesics of the curved space that the sun creates. They're geodesics in space-time. It's the helical motion that I drew. That is the straightest line in the curved space. That is a geodesic in the curved space-time about a massive object. So remember, we drew that helix. That helix is a representation of the geodesic motion in the presence of a massive object. That's the straightest line you can draw. And in general, a set of coordinates that allows you to describe all of space-time does not exist, and we'll see some times when that is a problem, and we'll actually have to pay attention to this. A better visualization of, in fact, the gravitational effects, the curved space not space-time, the curved space around a stationary gravitating object like a star is this so-called Flamm's paraboloid. And this actually is related to the curvature of space in the following sense. The space around a star is spherically symmetric, so you can break it up into balls, and you can assign each ball a size based on its area. And what we do here is to each, instead of this, we draw circles, and the circumference of a circle is 2 pi r, where the surface of that ball is 4 pi r squared. And if the space is flat, then the distances between the balls are the differences in their r's that you get from their areas. But in this curved space, the distances between adjacent balls are not given by the differences in their r's. In fact, there is a variation in the distance between them. And as you get closer and closer to the gravitating object, in this case, say a star, then the distance between adjacent spheres, or in this picture, circles, gets large. And the way we, relative to the change in their areas, and the way we do this here is we pull down the bottom of this sheet so that these two circles, if this were flat, these two circles, which have radii that are circumferences that are very close to each other, would actually be right next to each other, and we're extending it so the distance between adjacent circles is different. And this actually does represent, in a somewhat reliable way, the space around a gravitating object. So I've been very hand-wavy about how gravity is curvature. I can write you the equation. So here's what Einstein tells us. Here is Einstein's theory of general relativity, and the discovery that gravity is geometry is only the first step. The next step is writing the equation, which tells you that the way in which mass energy generates a source of curvature, it's a source of space-time curvature in the same way that electric charge is a source of electric fields. And when you change the distribution of energy and momentum, it is the curvature of space-time that is this field. The ripples in space-time are the waves in this field that carry the information off at the speed of light. And this is the equation. This is Maxwell's equation for gravity. It looks simpler, but only because all these symbols are confusing. We will not do anything with this equation except write it down, but I just want to write it down for you. This is Einstein's equation. These R-looking objects are bits of the Riemann tensor. They express the curvature of space at a particular point in space and time, the curvature of space-time. G, we know, that is Newton's constant. C is the speed of light. And this T object is the energy momentum stress tensor. This is our characterization of the flow and amount of energy and momentum at a given point in space and time, or at a given event. So at a given event, you have this acting like the electric charge, and this tells, this is a differential equation that tells the gravitational field how to respond. You can solve this equation. One of the consequences of this equation is that inertial motion, the motion of objects under the influence of nothing but gravity, is along geodesics of this curved space-time that you obtain by solving the equation. So just as Maxwell's equations imply charge conservation, these equations imply energy momentum conservation, but also the fact that objects upon which only gravity acts move along geodesics of the space-time that has been created. There is, of course, as always, there has to be a limit in which we reproduce Newton's theory, because Newton's theory has worked so well for us in describing, say, the motion of Earth around the sun and binary stars and so on. What is the limit? The limit is that if the curvatures are small, if you don't get too close to objects that are too massive, if the gravitational fields are not extreme, and if the speeds at which objects are moving are slow, then you reproduce Newton's formula. You can express, for example, the motion of a planet about a stationary star in terms of sort of some effective potential energy function, which will appear somewhat familiar. It's a function of r. It starts off with our favorite familiar term, minus gmm over r. This is just the Newtonian potential energy. It's got this weird looking thing. L there is the angular momentum. We'll see in a minute what that is. And then the first correction, there's a whole series of corrections, but the leading correction to Newtonian physics is this L squared over c squared r cubed correction. This becomes a little more sensible if you make the somewhat unjustified statement that the angular momentum is mvr. This is true for motion in a circular orbit. Plugging L equals mvr into this equation simplifies things a great deal. For example, L squared over 2mr squared becomes, let's write it out so we know what we're doing, so you don't accuse me of cheating. L squared is m squared v squared r squared over 2mr squared, and now I do all my handy-dandy cancellations. The r squareds cancel, one of the m's cancel, and this is a half mv squared. So this term, in the case of circular orbits, is a fancy way of saying kinetic energy. This term is Newtonian potential energy. This term, when you plug everything in, turns just into v squared over c squared times this term. And so this is the leading correction to Newtonian physics, and of course there are higher order corrections, but when v is small compared to c and the curvatures are not too extreme, we see that we reproduce precisely Newtonian physics. So good, we expect Einstein's theory, as we said, to reduce to Newtonian theory in suitable limits, and this is the suitable limit in which that works. And then the last thing I want to point out is that there's a complication in gravitational theory that makes the mathematics of solving Einstein's equation and understanding the structure of its solutions a vibrant and lively and interesting field of mathematical research as well as physics, which is a complication that is not present in Maxwellian electrodynamics. And the idea is this. Take the mass of, say, the Earth and the Sun, the Earth-Sun system. The mass of the Earth-Sun system, I claim, is a little bit less than the mass of the Earth plus the mass of the Sun. And the reason is that Earth is bound to the Sun. There's some negative gravitational potential binding energy between the two. Remember, if I took the Earth and the Sun very far away, as they fell, they would release energy. Having lost energy, that reduces their mass because mass and energy are equivalent. So the mass of the Earth and the Sun together is a little bit less than the mass of the Earth and the Sun separately, just as the mass of a helium atom nucleus is less than the mass of 2 neutrons and 2 protons. But that means that the gravitational field that the Earth-Sun system together creates is different from the gravitational field that would be created by the Earth and the Sun. There's some contribution due to the gravitational binding energy. In other words, since gravitational fields carry energy, gravitational fields gravitate, which is almost as if you had the photon, the particle that carries light, being a charged particle, so creating its own electric field. This would be like an electric field creating an electric field. This makes Einstein's equation, unlike Maxwell's equation, nonlinear. Superposition principle for waves does not hold. These equations are very complicated, and as I said, studying their solutions is an ongoing enterprise. We won't get to do a lot more of the meat of general relativity. As I said, the mathematics there is more than we can afford to do, but we'll see some of the consequences, and hopefully that'll be worth the effort to try to understand something.